Okay, let's have some fun with the concept of potential energy and use it to get us a result, namely the escape velocity for something to leave the planet Earth. And it's interesting that it's going to turn out, you'll be surprised at all the stuff that you don't need to know to get a really interesting number out of this. Now, to be careful, I'm thinking about a situation where we're going to ignore stuff like the Earth's rotation and also air friction. But you know, when you think about it, there's atmosphere is very thin, and I'll emphasize that in another question we'll ask ourselves shortly. But these are our assumptions, that we're just going to have a rocket, and it's going to have a very quick launch. It's going to be very ballistic. We're just going to shoot it up, and with some initial velocity. So fasten your seatbelts for that launch, and then see what's the minimal velocity it will take to escape. Now, it's kind of a philosophical thing, but when I say that, what I mean is this rocket has been flung off the Earth with that tremendous initial shot, and it goes away from the Earth, and you know the force of the Earth is pulling back on it, but it's getting weaker and weaker and weaker. And so I want to think about a kind of an interesting limit to consider. Suppose it was getting weaker, so weak in fact, that it just didn't have any effect at infinity. So you're infinitely far away. So the gravity, as you know, the force goes like 1/r², so it's going to go away if I go off an infinite distance away. But to make it the minimal velocity to get you escaping, we're going to say that it gets slower and slower and slower, and finally out there at infinity, it has no velocity at all. And that turns out to not be, you know, it might be troubled by taking that limit, but it turns out to work out very sweetly. Now, the approach I want to take is to emphasize how valuable it is to think about potential energy here. Now, there's one thing that you gotta know about potential energy. It's just relative to, like, the potential energy on Earth versus the potential energy out to Pluto versus the potential energy out to an infinite distance. And there's a very simple limit that we're going to take here that's very natural to take. Remember, while the force of gravity goes like 1/r², the potential is going like 1/r. In fact, I'll just write down that relation right now. The potential energy as a function of distance from the Earth, we'll call that little r, from the center of the Earth, as it turns out, is all you need to know, as long as you're always away from off the surface of the Earth, is going to go like minus g, mass of the Earth, mass of the rocket, divided by r². Okay? That's your form. Whoa, I blew it. It's 1 more. That's potential energy. Almost committed a crime there. So what we're dealing with is a situation where there's a constant. But like I said, it'll turn out to be super convenient to say, let that constant be 0. So that means that when you're infinitely far away, your potential energy is just a big fat 0. It starts out negative because you're down in a hole. You'd rather be at lower energy if you're rolling downhill, and it's negative as you get closer and closer to the surface of the Earth. And furthermore, we said at that moment in the rocket's flight, when you're out there in infinity, the kinetic energy is gone. No motion at all. Now, when we leave the surface of the Earth, let's do a little blow up here. Here we are at the surface of the Earth, at our launch point. That's where we're going to blow this up here and say, what's my potential energy going to be over there? Well, it's going to be, we know it has to be because you're off the surface of the Earth. So there, at that position, and now we'll call big R the diameter of the radius of the Earth. So my R, which is varying from the diameter, the radius of the Earth, all the way off to infinity, at that particular value, surface of the Earth, you're going to have the same formula, minus g, me, rocket's mass, then big R. Now, the next thing we want to know is, what's our kinetic energy, okay? Well, that's the thing I don't know. That's what I'm trying to solve for, and I know that because the kinetic energy is just 1/2 mass of the rocket times the escape velocity. And that's why I said that's the thing I want to know about. I want to know how fast it has to move to get off there. Oh, by the way, you notice there's no vectors here. It's really kind of neat when you deal with energies. You don't have to deal with vectors. That's kind of cool. And in fact, that's one of the lovely things about the use of energies here. So the total energy up here, at this point over here, the total energy we'll call that T, U plus K, is just a big fat zero. But that's the same total energy. Energy gets conserved here. And that force, by the way, you can't always have its potential energy. Just to remind you, for all forces like friction forces, there's no potential. But gravity forces, you can have a potential for it. In fact, that's what's meant by a conservative force. So over here at the surface of the Earth, T at the surface, that's at little r equals infinity, but at little r equals the radius of the Earth, what you're going to have is the same number. We say it has to be energies conserved. That's going to be our potential energy at the surface, which is minus G ME MR divided by R, okay, plus the kinetic energy bit. And that's kind of good. It looks good here because I've got a positive quantity over there, the kinetic energy, 1/2 MR VE squared, plus this negative potential energy. So that could cancel. That looks nice. It could cancel out and give us exact zero, which is exactly what I have to have. So that's an equation there for VE. There it is. If you want, you can now you can just solve for that, okay? Let's go ahead and just solve for it, that equation for VE. And I'll write it all down here because I'm going to have, well, first let me simplify. 1/2 M rocket VE squared equals G ME M rocket over R, okay? That's what I'm saying. And that's looking good. I can now factor out M rocket there. So I have an expression. VE squared is going to be 2 big G ME mass of the Earth times R. Now, here's where a lazy physicist can really make some progress. The reason is because, and I think you may have seen this one before, we can talk about the magnitude of the force of gravity at the surface of the Earth. And we can think of it two different ways. We can say, well, it's going to be given by, I'll write this all down here because I'll need this result in a second. Make a nice substitution here. I can think about the force of gravity at the surface of the Earth on that rocket two ways. It's pulling down, say, I'm at the, let's suppose I shoot it off from the top of that Earth. It could be seen as minus mr times little g, or it can be seen from this universal law of gravity point of view as minus big G mr me divided by r squared, radius of the Earth squared. This is at the surface of the Earth, so that's good. And that means I can now look at this combination that appears down here in a new light. Look at that. Oh, r squared, whoa. But let me write this out a little differently here. Instead of writing r squared, I'm going to notice that this combination here, and also I can factor out the mr. Okay, I did that before, I'll do it again, and the factor of 2. Don't you hate it when people just erase like that? Okay, so now what I'm saying, the thing that I need down here, something that's about the universal force of gravity, the gravitation constant, ME, mass of the Earth, and the radius of the Earth, well, that's the combination I need over here, and it's just given by G times R. So that is the thing that I want to have here, and it's a little, saves me a little brain power of working this out, because I happen to know what little g is, and I can look up the radius of the Earth, not a big deal. So very little looking up going to go on here, because I recognize this is a combination of something I would like to have. So now I can just substitute this into here, and here's what I get. I'm going to say that VE squared is going to look like 2 little g times R. That's what I found out. And now I can solve for VE. Just unsquare that thing. Okay? So here we go. It's going to get unsquared, and voila, you can't get more compact than this, 2g radius of the Earth. Okay, so now let's just look up this stuff. The radius of the Earth happens to be given by 6.4 times 10 to the 6 meters. Okay, it's also happens to be 4,000 miles, which is why I got introduced to it in the first place. And then I can just substitute in here for VE, and it ends up, when you plug in the numbers, because of course, remember, little g is 9.8 meters per second squared, and units are looking good, because I'm gonna have distance squared here, divided by second squared, but I take the square root, so that's a velocity, or speed, I should say. So subbing all that stuff in there gives me a value for VE. If you like it in kilometers, it's going to be 11.2 kilometers per second, or if you like it in miles, it's about 7.0 miles per second, which is pretty darn zippy. And that rocket leaves the Earth, it's moving there. So that is actually your escape velocity to get you off the Earth and never come back. You will rise up, but you'll never fall, because by the time you get to the point where you would descend, because you're hitting that turnaround point, you're already infinitely far away. So that's the minimum velocity. And to get off the Earth, anything faster would have you moving out there at infinity. And furthermore, remember the assumptions. We're not dealing with anything spinning about the Earth, which actually helps you launch satellites and or rockets. And on the other hand, we're ignoring air friction.